So, hi everyone, I'm Geraldo. I'm a PhD graduate at the Safari Research Group, and today I'm going to talk about our work Proteus, achieving high performance processing using DRAM with dynamic with precision, adaptive data representation, and flexible arithmetic. So let's get started. So before I start, I'm going to give a brief overview of what this work is about. So processing memory architectures are architectures that aims to alleviate data movement bottlenecks by moving computation to where the data resides. In particular, processing using DRAM architectures uses the analog operating principles of the DRAM cells themselves to perform book bitwise operations. So even though processing using DRAM architectures can accelerate many application domains, they suffer from three main issues caused by the naively use of a bit serial execution model. Those being suffering from a rigid and static data representation format, leading to unnecessary computation in the presence of narrow values. Second, they have a throughput-oriented execution model with limited latency tolerance. And third, they suffer from a scalability challenge for high-precision arithmetic operations. Therefore, our goal in this work is to mitigate those three issues caused by an naively employ a bit serial execution model for process using DRAM architectures. To this end, we propose Proteus, a data-aware runtime framework that dynamically adapts the bit precision for a given processing using DRAM operation, and based on that, chooses and uses the most appropriate data presentation and arithmetic algorithm implementation for that target operation. So we extensively evaluate Proteus, and we observe that significantly improved performance per area and also provide energy gains compared to state-of-the-art process using DRAM systems, high-end CPU and GPUs, while incurring small DRAM and CPU area overheads. So this is the outline for this talk. First, I'm going to briefly introduce processing using DRAM architectures and cover a brief DRAM background. Then I'm going to elaborate more on those three main issues that I mentioned earlier for processes using DRAM architectures, which are going to lead me to our design, Proteus. Then I'm going to give a brief overview of our evaluation results, and then finally I'm going to conclude. So let's get started. So as I mentioned, processing memory architectures are architectures that aims to alleviate data movement bottlenecks by moving computation to nearby where the data resides. So such architectures can be implemented in two main different ways. Processing near memory architectures adds logic near the memory arrays themselves for computation, while processing using memory architectures uses the analog operating principles of the memory cells themselves to perform computation. So in this work, we mostly focus on processing using memory architectures, in particular is realization using DRAM. Before I introduce process using DRAM architectures, I'm going to give a brief background on DRAM organization and operation. So DRAM chips are hierarchically organized. On the bottom level, we have what's called DRAM mat, which is a 2D array of DRAM cells. So rows in a DRAM mat shares a word line, and columns share a bit line. Columns are connected to a set of local sense amplifiers, and rows are connected to a local row decoder. Multiple DRAM mats constitute what's called a DRAM subarray. The many DRAM mats in a DRAM subarray are indexed using a global row decoder, which propagates the target row address across the many DRAM mats using the global word line. To move data outside the DRAM mat, a DRAM subarray uses a global sense amplifier, and to move data outside the DRAM subarray, a DRAM chip uses the I/O logic interface. So the memory controller issues two main commands to access data from the DRAM chip. So to access the DRAM row, the memory controller issues activate command to the DRAM. On receiving the activate, the global and local row decoder accesses the word line to the target row, connecting the DRAM cells to the bit lines. Then the sense amplifier senses the perturbation causing the bit line, amplifying and latching the data from the DRAM cells. There, the memory controller issues a read command to read a column of data from the previous latched DRAM row. The read command moves the target DRAM column from the local sense amplifiers to the global sense amplifier and filing to the memory channel via the I/O interface. So the operating principles of DRAM chips can be used to implement book bitwise operations inside the DRAM chip itself. For example, row clone implements in DRAM row copy operations by issuing back-to-back activate commands to the DRAM chip. The first activate copies the source row into the local sense amplifier, and the second activate connects the destination row to the local sense amplifier, which allows the previous latched source row to be written back to the destination row. Ambit implements majority operations in DRAM by simultaneously activating three DRAM rows at the same time. When three rows are activated, they simultaneously perturbate the bit lines based on the DRAM cells content, and this allows for the local sense amplifier to compute a majority of three of the values stored in the DRAM cells. In order to implement book bitwise arithmetic operations, the authors of SimDRAM implement a three-step framework that maps the desired operation into series of in-DRAM row copies and majority of three operations. I will illustrate how this process works using a RIP carry adder. In order to add two arrays, A and B, with as many data elements as DRAM columns in a DRAM subarray, each element being a 1-bit data value, SIMDRAM converts a AND or NOT based RIP carry adder into its equivalent majority NOT based circuit. Then it issues a in-DRAM triple row activation in order to realize the required majority NOT operations one majority gate at a time. In the end, one DRAM row will hold the generated sum and carry out bits for the 1-bit addition operation. This process is repeated for all individual AND bits in an input data world. Hence, SIMDRAM transforms a DRAM chip into a very wide bit-zero SIMD engine. So prior works have shown that commodity off-the-shelf DRAM chips are capable of performing bulk bitwise operations without hardware modifications. And I invite you to check our paper for more details on those. So let's look at the limitations of such processing-using DRAM architectures. So those processing-using DRAM architectures often use the bit-zero execution model, operating on each bit of data individually. However, a naively employed such execution model introduces three main challenges. First, processing-using DRAM systems rely on static data representation, linked to costly operations over incidental narrow values with small dynamic ranges. This results in wasted energy and poor performance. We can mitigate this issue by reducing the bit precision of the target process-using DRAM operation, focusing on computation over consequential bits. Second, while process-using DRAM systems employ a throughput execution model to high latency operation latency, they do not reduce the latency of individual process-using DRAM primitives. We propose map individual bits across multiple DRAM subarrays to execute them in parallel, hiding the latency even for small data volumes. This also allows for the implementation of bit parallel process-using DRAM arithmetic operations. Third, bit-zero arithmetic scales poorly with the bit precision, causing high precision operations to significantly degrade performance. We address this issue by adopting alternative data representation formats for high precision operations. I will briefly expand on each one of those issues next. It starts with the region and static data representation. So it's well known that many applications display what's called narrow values, which is our data with small dynamic range stored in large data formats. For example, let's assume that you have a data element A that stores value 4 in the 3 least significant bits. However, the minimal standard data format available in high-level programming language such as C is 8 bits. Thus, the remaining 5 most significant bits of such data elements will be leading zeros. When adding two values that display narrow values using a bit-zero execution model, the leading zeros will not contribute to the dynamic range of the produced output. Yet, such sequential bits will be processed by the bit-zero engine, wasting memory cycles and energy. In our work, we quantify the amount of narrow values present in real applications. To do so, we provide the required bit precision of data on loops of 12 real-world applications. We define as the required bit precisions, such as the minimum number of bits required to represent input operands. In our box plot over here, whiskers extend to the largest and smaller bit precision values. So we make the key observation that applications display a significant amount of narrow values, where the bit precision can be reduced from 32 bits to 20 bits on average. So in order to solve this static data representation issue, we propose to dynamically identify and skip inconsequential bits in narrow values during bit-zero operation. Doing so, allow our process-using DRAM system to save DRAM cycles and also energy for process-using DRAM computation. Next, we are going to discuss the next issue, which is the throughput-oriented execution with low latency tolerance. So we observe that process-using DRAM operations are inherently slow due to the need to operate on each bit of a data word individually. So this issue is further exacerbated by the inter-bit dependence present in bit-zero arithmetic operations. I will illustrate this issue by showcasing a 2-bit process-using DRAM addition operations of 2 plus 2. A process-using DRAM substrate stores all data bits of the input data words vertically within a single DRAM subarray. During operation, the majority NOT operations required to implement the process-using DRAM addition will be first performed over bits 0 of the data word. During this process, the carry from bit 0 will be generated and propagated to the input carry that will be used for bit 1. Note that the inter-bit dependence forces the serialization of process-using DRAM primitives of data words when they are placed inside a single DRAM subarray. Only after the inter-bit dependency is satisfied, the majority NOT addition over the bit 1 can be executed one majority operation at a time in a serial manner. To reduce the latency of process-using DRAM operations, we aim to have bit-level parallelism to execute independent process-using DRAM primitives concurrently across different DRAM subarrays. In the bit serial addition example, after the carry from bit 0 is propagated to bit 1, the yellow and red majority gates here becomes bit independent and can be executed concurrently. In order to exploit such key idea, Proteus implements a specialized data mapping called 1 bit per subarray, where bits of a data word are scattered across different DRAM subarrays for parallel execution. In the example, instead of storing all bits on the input arrays in a single DRAM subarray, Proteus stores in subarray 0 bits zeros and subarray 1 bits 1 of the input arrays A and B, thus allowing both subarrays to operate concurrently over bit-independent values. Besides that, Proteus leverages a high bandwidth inter-subarray interconnect that allow us to move data required during carrier propagation between neighboring DRAM subarrays. Let's see how Proteus exploits bit-level parallelism in your 2-bit bit serial addition example. So first, Proteus executes the carrier-generated majority gate for bit 0 in subarray 0. Next, Proteus uses the inter-subarray interconnect to copy the generated carry from subarray 0 to subarray 1. Afterwards, the bit independence is achieved, and the remaining majority operations across bit 0s and 1s can be concurrently executed in subarray 0s and 1, respectively, hence reducing overall latency. Finally, let's look at the third issue caused by the bit serial execution model, which is a scalability challenge for high-precision operations. So due to the inter-bit dependence, bit serial arithmetic operations scales linear for addition and subtraction operation and quadratically for multiplication and division operations, resulting in higher latencies as the bit precision increases. To solve such an issue, we propose to use alternative data representation format for high-precision processing-using DRAM operations. In particular, we use in this work the redundant binary representation format. In such data format, each bit position is represented by 2 bits that can take a value of -1, 0, and 1. For example, the number 3 can be represented using 4 bits, such as 0, 1, 0, and -1. Because of its redundant nature, implementing RBR-based arithmetic, the carrier propagation is limited by at most 2 places, making the latency of processing-using DRAM operations using such data representation format independent of the bit precision. Based on these key ideas, we propose Proteus. Proteus is a data-aware runtime mechanism for efficient process-using DRAM execution. Proteus adapts the bit precision in DRAM implementation and data format based on the target input data transparently from the user. Proteus is composed of 3 main components implemented in the memory controller: a parallelism-aware microprogram library, a dynamic bit precision engine, and a microprogram select unit. I'll briefly elaborate on each component next. First, the parallelism-aware microprogram library is a collection of hand-optimized implementations of different processes using DRAM operations called microprograms. Each implementation has different trade-offs in terms of performance based on the target bit precision. Second, the dynamic bit precision engine aims to identify the dynamic range of evicted cache lines belonging to the target processes using DRAM operation by scanning data within evicted cache lines that belong to the process using DRAM memory objects, aiming to identify the largest values in such cache lines. Third, the microprogram select unit aims to identify the appropriate bit precision based on the previously identified largest values belong to the memory address involved in the processing using DRAM operation. Based on this calculated target bit precision, the microprogram select unit probes the parallelism-aware microprogram library to identify what is the best in DRAM realization of the target operation based on the target bit precision. Due to time constraints, I refer you to our paper for more details related to Proteus, including detailed hardware implementation of bit parallel processing using DRAM operations, Pareto analysis for processing using DRAM operations, data format conversion procedures, system integrations, and how we can implement this framework for float point operations. For all of that, please check our paper. Next, I'll give a brief overview of our evaluation results. So we compare Proteus to a high-end CPU, GPU, and a prior process using DRAM system, SIM-DRAM. We use 12 workloads from 4 benchmark suites, and we evaluate CPU normalized performance per area and energy reduction. First, in terms of performance per area compared to the CPU, GPU, SIM-DRAM, Proteus with only its dynamic bit precision engine enabled, Proteus end-to-end design can lead to significant performance improvement. We observe that such performance improvement comes mostly from its dynamic bit precision engine. Second, in terms of energy savings compared to the CPU, GPU, SIM-DRAM, Proteus only with dynamic bit precision engine enabled, Proteus end-to-end design leads to significant energy reduction compared to memory-centric and processor-centric architectures. So in our paper, we have much other analysis, including Proteus with statically identified narrow values, data mapping and representation format conversion overheads, performance of float point operations, Proteus versus tensor core in GPUs, and area analysis. For all of that, I invite you to check our paper. So next, I'm going to briefly conclude. So in this talk, we propose Proteus, a data-aware runtime framework that dynamically identifies the bit precision, and based on that, chooses and uses the most appropriate data precision and arithmetic algorithm implementation for a target processing using DRAM operation. We extensively evaluate Proteus, and we observe that significantly improves performance and energy compared to processor-centric and memory-centric architectures, while incurring small area overheads on top of the DRAM chip and CPU die. Thank you very much for your attention. I'll be glad to take any questions. Thank you. Very intense.
So just a very, very general question. So processing memory is always with potential bandwidth, but you've been talking about latency. Is that because it's latency? Finding memory.
So here the problem is it's not necessarily that related to bandwidth. Actually, it's just that when you're doing a processing in memory, as I mentioned earlier, using DRAM activations, you can think about the DRAM activation latency as your clock of your processor, and activation latency is very high for DRAM chips, like around 13 or for 15 nanoseconds for modern DDR5 or 4 devices, right? So if you don't if you don't do as fewer activations as possible, the latency of your operation is just going to scale because activation latency is very high. So here is where the latency is coming from, not necessarily from bus widths or moving the data around inside the DRAM chip itself. It's mostly because activation latency is very high. Yeah.
So how is the processing to get such
Yeah, that's a great question, actually. So that is, didn't mention earlier, but in the background, I mentioned this framework that implements arithmetic operations using this three-step framework called SIM-DRAM. It's a private work from myself. And over there, basically, we implemented 16 different complex operations that can be used for those benchmarks that I'm showing over here. And those include common operations like addition, subtraction, division, multiplication. And a lot of those are based on generating a circuit that is required for that operation and mapping that circuit into sequence of majority of 3 or not operations, because the set of operations is a Boolean complete. So we can implement, in theory, whatever operation that we need. So that prior work proposes those 16 implementations of in-DRAM arithmetic operations. And then there was another follow-up work from myself called MIM-DRAM, presented in HPCA last year, that has we implement basically a compiler routine that can take a C application, identify codes that are suitable for this execution model, and generate the code appropriately. So we use basically that compiler infrastructure to map those 12 applications down to those 16 arithmetic operations that I mentioned earlier. So it's a combination of a lot of moving pieces, basically. Thank you very much for your attention.